And how ironic that we're actually talking about ionic equations, and we get to revisit one of our favorite topics, PPT reactions. So that means we get to look at this table again, or use this table again. Now remember, you have access to this table. Unfortunately, you don't have to memorize this table. I know a lot of you are like, gosh darn it, I just wish we could memorize this and just not have to look at it anymore. And I understand your dilemma here. But just to refresh your memory, the left column actually deals with your non-metal, and these will be the only non-metals that we'll work with. So don't freak out and say, could you please give us more? No, I can't. So we'll just work with these. And then your metal, or your positively charged ion, is in the middle. So you always look at your negatively charged ion first, and then use the lines. So like, for example, if you had sulfate, if you had, say, let's say sodium sulfate. So you find your sulfate and come across, is sodium listed on the top? No, so you go to any other positive ion and soluble. What does soluble mean? It's clear, very good. So it means that all the ions dissociate, there's nothing happening. I start off with a clear solution. When I pour it together and mix it up, it still is clear. The not soluble is what you're looking for there to be a reaction. That is our PPT. So if you have a not soluble combination, and you could have one or maybe two, but if you have a not soluble combination, then you have a reaction. You have something going on. And we did this a long time ago, before the deep freeze, before the polar vortex hit us. So it's been a while, but it's okay. So that's the table again. I can't remember, were there any blanks there? No. There's a blank. So again, an insoluble substance is your PPT. So you can recognize that you have a PPT is you would circle it because you're forming the PPT, which means that you're forming a solid. Now you do not have to write aqueous for each of these. All right, so we'll know that it's aqueous because when you do the ionic equation, you'll actually break it apart into its ions, just like what you did on the homework, or a lot of you did on the homework last night, or some of you. Okay, so we still circle our PPT. These are still double replacement reactions, so unfortunately nothing new here. So here's the process in writing an ionic equation. It'll make a little more sense once we actually start doing a couple examples. I personally like to write out the equation as is, just like what we did when we were working with double replacement reactions. And then I would go to this step here, which doesn't look right. There we go. So we would go to this step here. But again, it'll make a lot more sense when we start to do these. Now this image here is actually showing what is happening or what is occurring. So I have two different solutions, and it looks like in this one I have silver nitrate and potassium chloride. When I mix the two solutions together, well, the nitrate and the potassium ions aren't going to do anything. They like to be soluble. And if we say that we have a bunch of nitrate and potassium ions in solution, did we talk about what those ions were called? Okay. You can say, or actually treat it like if you're an athlete and there's a big crowd, there's a few people in the crowd that actually think that they're involved in the game. They think that they can sway the game or cause you to perform better because they're yelling and screaming as hard as they can at you. Usually parents, they're awesome for going to sporting events. But no, these are spectators. They're simply little voyeurs in chemistry. They have no responsibility of what is happening. They just think they're having a good time by being involved. So we allow the spectators to be there, but there it is. So the spectators think that they have a part in the game, but really it's you that has the part in the game. I love it when parents start yelling. It's awesome. Is nobody knows what I'm talking about, right? Okay, I got you. No? She does or doesn't? Does yell and scream?
Yes.
Oh, okay. Does anybody's parent not yell and scream?
Mine.
She doesn't, I was about to say she doesn't love you.
She doesn't care.
All right. Net ionic equation, we will also not only write the ionic equation, but we will write what's called the net ionic equation. The net equation actually is the reaction that is the action, so to speak. So when we looked at, say, up here, well, the nitrate and the potassium aren't doing anything because we started off with potassium ions, we finished with potassium ions. We started with nitrate ions, we finished with nitrate ions. So if it looks the same at the end as the way we started, then nothing's happening. So we're looking for a change. And when we talk about changes, normally what happens is, especially for this type of reaction, we form a PPT. Now the charges don't change. In other words, silver still has a +1, chlorine still has a +1. But what's happened is the silver and the chlorine have come together and formed a new substance. So we will write what's called the net ionic equation, but the net equation is the equation that shows that something is happening. So when you get into AP chemistry, we'll talk more about net equations. So here's an example. Awesome. You can take a look at that later. Here's a practice problem. Let's take a look at this. All right, so here's the practice problem. It says, write an ionic equation for the reaction that occurs when equal volumes of a 5 molar solution or solutions of magnesium sulfide and sodium carbonate are mixed. Now, as a sidebar, we don't care about this information here or here, all right? You're not doing any calculations. So we're simply writing the ionic equation and the net ionic equation. So don't worry about all the distractors that are in there. So we have solutions of magnesium sulfide and sodium carbonate. Now here's what I suggest. I would write out the equation. So we have magnesium sulfide. So we have Mg and S. Because how do you know it's S and not SO4? Good. It ends in IDE. Very good. So pick up on those things. And actually, let's scoot you over. And we also have sodium carbonate. So sodium and carbonate. Now, the next thing that we need to do is balance charges. And again, this is me, we haven't started doing the ionic equation yet because I want to balance these things out first. What's the charge on magnesium? +2, very good. Charge on sulfur? -2. So that one's good as written. So we're happy with that one. Sodium, what is that? 1. +1. Carbonate? -2. So what does that mean? We need 2 sodiums. Okay? All of these reactions are going to be double replacement. In other words, partners are going to flip. So what will we form on the other side? Put magnesium with carbonate, and we'll come back to that. And also we're going to have, and remember, put metals first. So we'll have sodium and sulfur. Now again, we already have the charges. Sodium is a +1, sulfur is a -2. So how many sodiums should we have? 2. Good. Okay. Bless you. So the magnesium and the carbonate are also +2 or -2 respectively there. So we have our charges balanced. Now the next thing we want to do, or what I like to do, is balance the number of atoms. How are we doing? We're good. We're balanced, right? Because we have 1 magnesium, 1 sulfur, 2 sodium, 1 carbonate. Good. All right. Now, once you have your equation, I promise you're going to have a reaction. Something's going to take place. So don't just go like, oh, okay, no reaction, I'm done. There's going to be something happening. That's why I asked this. All right? So we're not. There are no reactions here. So we want to find out, okay, who's dancing here for us? All right, well, go back to your table. And we had sodium sulfide, so let's look at that one first. So find the sulfide. There's sulfide. And we come across, is sodium an alkali ion? If you're not sure, look right there.
Yeah.
Okay, it is. It's group 1A. So you go, oh, soluble. What's that mean? It's clear. Stayed clear. Okay. And then the next one was, what was it? Magnesium? Yeah, magnesium carbonate. So find carbonate. Oh, there it is, yeah. So go to the top row. Is magnesium an alkali ion? It's in group 2A. So go to any other positive ion. Hey, we got a not soluble. So that means we have a PPT. We have something happening, which is good. We want something to take place. If you think they're both soluble, you need to start over or reevaluate your life again here. All right, so this is the step that I recommend. You don't have to show this step, but I'd recommend it. Here is where we actually start to begin the ionic equation. Okay. We haven't even started anything yet, so write small. Okay. In other words, the ionic equation is showing these as ions unless you form a PPT. So let's show that. So we have our magnesium, and we'd show our charges, so +2. We have a sulfur, -2. We have 2 sodiums with a +1 charge. We have 1 carbonate with a -2. So those are your ions on the reactant side, or the left side. Okay, so ionic equation, you show the things as ions, if they are ions. In other words, everything that I give you on the reactant side, I promise will be soluble. I promise. And then, since we form magnesium carbonate, we'll keep that together because we have something going on. All right. It's nice, but not required, if you wrote a little S there. What does that mean? That we actually have a solid, or PPT. Okay. You don't have to because it is together. And there's no charges that are shown on this. That's why you do your balancing up here, so you don't show any charges accidentally down here. And then you finish off by saying, okay, well, I still have 2 sodiums with a +1 charge and sulfur with a -2. Okay. So that sodium looks the same on both sides. The sulfur looks the same on both sides. Because sodium and sulfite are what? They're spectator ions. Very good. They think they're having fun and involved, but really they're just spectators. Yes, Sage?
When you're writing the last equation or whatever, do you have to put, well, no, like the beginning of it, or just like everything? Do you have to, do you have to write the charge?
You must write the charge. Good question. The charges must be shown unless you form a PPT. And then make sure that the charge is actually balanced. But they equal 0, so there is no charge shown there. Okay. And then the last step is the net ionic equation. And in this step, we only show those who are dancing. All right. So we're forming magnesium carbonate. Who makes up magnesium carbonate? Magnesium and carbonate. Now we're going to have a quiz over this on Friday. Do you think you could do this?
I hope so.
Yeah. This is some tough stuff, right? Oh, Caitlin's not having fun. Already?
Yes.
Well, you shouldn't drink so much.
I'm sorry. I was thirsty.
You need a bigger bladder.
Yes.
On magnesium carbonate,
Uh-huh.
the green number right there, I'm not sure.
This is S for solid. You don't have to show that, but if you wanted to show that, that's fine. The reason why I put that there, just kind of like a reminder that we do have a PPT. Don't show charges here.
Why did you just put energy in the C?
Why did I do this?
Yes.
This is the actual ions that are involved in making the PPT.
Oh, okay.
So the ionic equation is everybody, including spectators. The net equation only shows those which change or involved. Okay. Everybody have that? That one set? Pretty easy, right? All right, we'll come back to that guy in a second. Is there a what? All right, so let's see here. So part of the homework is the 2's. Oh, we're almost done. It's so close. We're almost done. All right. Other reactions of solutions don't always form a PPT. And this will actually have some more significance in a couple of weeks when we talk about acids and bases and do a neutralization reaction. This is a neutralization reaction. Where here I have sodium hydroxide. Here, let me write it out here. I have sodium hydroxide, which is a strong base. And if I take a highly concentrated, high molarity concentration of sodium hydroxide, pour it on my arm, it'll eat my skin away. It'll do some really bad things to my arm. So don't do that at home. Then I also have hydrochloric acid. If I take a high concentration, high molarity of that, pour it on my other arm, that's going to do some really bad things to my arm as well. But if I mix these two together and say, okay, I have the hydrogen, get with the hydroxide, what does that form? Water, very good. And then if I put sodium with the chlorine, what does that form? Sodium chloride. So what I've essentially done is made ocean water or seawater. So I could take those things that I could pour on my arms and do some really destructive damage, or I could mix them together and drink salt water. I wouldn't recommend it, ever. But what's happening is it's a double replacement reaction where the hydrogen is attaching itself to the hydroxide to neutralize these nasty hydrogen and hydroxide ions, which would be destroying my arm, which is not a good thing. Okay? That's what happens in your stomach all the time. You have this hydrochloric acid in your stomach. If you get acid reflux, some of you might take Tums. What is another one? Not the generic or not the prescription things, but Tums is made up of calcium hydroxide. So when you eat a Tums and it says it's got calcium, well, the calcium doesn't do anything, but it's the hydroxide that reacts with the hydrogen and forms water. So it neutralizes your acid reflux. Okay, it's chemistry. So when you eat that chalk, you're like, nah, but you feel better, so it's all right. So here's what's happening. Even though we're not forming a PPT, we're taking things that are wicked by themselves and making something that we all enjoy. At least we should all enjoy. And this is a neutralization. Notice that I'm forming not an aqueous solution, but I'm forming a pure liquid. So since I'm forming a pure liquid by combining the hydrogen and hydroxide, and I hate to tell you, this is the only scenario that this is going to happen for you guys. So if you form water, you have a reaction. So remember, you're always going to have a reaction taking place. And if you go and look on the chart and you say, well, the sodium and chlorine are soluble, the H and the OH are soluble, it's water. Don't say it's a no reaction. It's actually a very important reaction to neutralization. So if you have the formation of water, make sure you include that. How do you know? Because H2O is formed. Or you'll have hydrogen ions, and you'll have hydroxide ions. So let me see, are there any more blanks here? But there's a practice problem. So let's take a look at that practice problem. So it says, write the ionic equation for the net and the net equation for the reaction of sodium hydroxide and hydrochloric acid. Sounds like something we just did. How about we change this to lithium hydroxide? Let's mix it up here. Change it a little bit, mix it up. So here we have lithium hydroxide, and again, I'm changing that for those of you who are just joining us, and hydrochloric acid. So what will my products be on the other side? Good, H2O, and if you want to write it as H2O, that's fine. HOH is the same thing. The reason why I write it as HOH, that's actually the proper way to write water because of the hydrogen and hydroxide. When you put those together, you make HOH. All right. And what else is formed here? Lithium chloride. Good. And I'm going to tell you right now that lithium chloride is soluble, so there's not going to be a PPT. However, there might be a PPT, and if a PPT is formed, you not only get to write a net equation for the water, you also get to write a net ionic equation for the lithium chloride. Two of them. Two for the price of one. All right, is this balanced? Yes. And we know that we have something going on because we have a liquid that is formed here. Not a PPT. Don't write PPT there. It's a liquid. It's an L. That's an L. Sorry, it's a cursive L. Cursive L. Sorry, I don't write in cursive very often, so.
Yeah. Oh yeah.
I thought an E would look like that.
That's what it's like.
Is that your E?
No, that's a sideways L.
It is a sideways L. Thank you. All right. So then to write the ionic equation, pretty easy. And then we form pure water and lithium chloride. So again, who are my spectators? Lithium and chlorine. In other words, you know it's a spectator because the way it started is exactly how it ends. Okay? And then the net equation, how would that look?
H plus OH.
And if you left it as OH plus H, that's fine, just don't write OHH. But to keep you from doing that, if you wrote it like this, that's cool. Keep you from doing something dumb there. Yeah.
So why didn't we do the whole PPT thing?
There are no, I didn't do any PPTs because we have a group 1A metal, and anytime you have a group 1A metal, you're never going to have a formation of precipitate, but
So neither of them are.
none of them form PPT, but just, I want to make you happy, Sage. So let's go back and check, because you should check if you're not 100% sure. So if you find your chlorine come across as lithium, one of those four, so go to the next row, side. Okay, so you still check just in case. But what I don't want you to do is come over and go, okay, well I have OH and, oh, H is in the first column, soluble. Yeah, but it also forms pure water. That's the more important thing. Okay, so if you don't have a PPT, but you do form water, you have a reaction. Is that what you're going to ask?
Basically.
Perfect. All right. And then the homework? Right there. 2s and 3s, I believe. Yeah, not too bad. Look at all of that. Oh,